Hello, students. Today we would like to talk about some of the results that we can glean from working with the definition of derivative. Geometrically, it is a very convenient tool, and we will find it to be much more rewarding as we learn certain theoretical aspects about it that give us very nice differentiation theorems. Let's just recall that the derivative defines the slope of the tangent line to the function at a single point where it exists. And so we found that using the definition of derivative was very similar to that of using the definition of limit. Lots of algebra, a little bit more tedious, but in the realm of abstraction, we can actually produce very useful formulas that we can apply to functions that possess certain characteristics. So with limits, we would have, for instance, if we needed the limit of a product, we could apply the product rule for limits. And if we needed, for instance, the limit of a sum, we could apply the sum rule for limits. And then, of course, we learned certain aspects about limits that made the computation very simple in many cases. So if you think about the definition of derivative, there are several ideas that we need to consider. We need to talk about functions that are constant. We need to talk about just the power rule for functions. For instance, if you have f of x equal x, or if you have f of x equal to a power of x, how do we do that? And there are two rules that remind us of the limit theorems that I've said before. The constant rule, for instance, if you have a constant multiplied by a function, what can you do with the constant? And if you have a sum or difference of functions and you want to take a derivative, is there a way to push that forward that makes it easier? And then the last idea we want to discuss is to look into the realm of sine and cosine derivatives. Those functions are extremely important in the calculus. And so if we can understand those two functions, then we get the results for the others if we move the theory of the derivative forward. So again, we're building the basic blocks for differentiation theorems that will allow us to move forward in a way that gives us confidence and computational ability. So let's get started with some of the basics here. Now, like I said before, let's just go ahead and get the ball rolling with a constant function. So we can suppose that f is just equal to alpha, where alpha is a fixed real number. And by fixed real number, I often say that we mean constant. So we need to be able to move between the two because both expressions are important. So we might say with more detail, we say if we use the independent variable to be x, we say f of x equals alpha. And then, of course, if we're not restricting the domain, we might as well say the domain of f is all real numbers. Of course, we have the luxury to restrict the domain as we need. So now what we want to do is look at this in terms of computing a derivative. So we'll use our second form, which we found to be very useful. So now we'll just say, take C to be an element of the domain of F, so just a real number. When we do this, we know that the function must be defined at C, but we don't actually know until we do the computation what the form is for the derivative. That is C included in the derivative? We have to look at what we get. That is, look at the result, and then we can analyze which C will make sense. So we have f prime of C equals the limit as x approaches C. Same thing, f of x minus f of C divided by x minus C. But now this is actually pretty simple. We know f of x is just alpha for all x. So we can fill in the values for f of x and f of c. We have alpha, and of course, the function is constant, so f of c is also alpha. And we divide by x minus c. These computations are good just to go through, basically because they're not super complicated. I've shown you many problems that I've worked out that have plenty of steps, and they're long-winded just because of the immense amount of algebra. But seeing this is kind of like looking at the limit definition for the first time. I really do want it to sink in, just as I do everything. But of course, now alpha minus alpha is 0. So this is just 0 divided by x minus c. Now, if you don't want to overdo the parentheses, you don't have to use these. It's pretty clear, but sometimes it helps for just to make sure you're understanding that you're applying the limit to this function. But of course, 0 divided by x minus c is non-zero because x is only approaching c. So we have the limit as x approaches c of the 0 function. And of course, the limit of a constant is just a constant. So what we see here, and this is not a surprise, the derivative defines the slope of the tangent line to the function at a particular point. And we know, at least geometrically, that constant functions do not vary with x. And we picture their graphs as horizontal lines or segments if the domain is restricted. And so this doesn't surprise us at all. That just defines a line with 0 slope horizontal. So this is, I'll just say this is consistent with what we think about the graphs of constant functions. So here's a result. So, and we will use this. So basically now, when we have a constant function, the derivative is 0. Remember, the limit of a constant function is said limit. That is, when you look at the derivative, you automatically go to 0. If you're taking the limit of a constant, then you get the said constant. So notice here, we have the limit of a constant, which is said constant. But we started with the difference quotient. And the difference quotient was built upon a constant function. So now we can say that and I'll just write this down, the derivative of a constant function is 0. So that's really easy to remember, but sometimes confusing to negotiate when you're thinking about just standard limits of constants and then the derivative of a constant. So just keep that in your mind, speak it, tell everybody about it. It'll help you to remember it. Now, let's look at a very simple example. One thing that we find to be of extreme use to us are power functions. That is the polynomials, the ring of polynomials has endless applications in mathematics and science. you spend great amounts of time studying the quadratic function. It is essential. And so we think about algebraic functions. We think about the square root of x. We've already dealt with those. Power functions are basically building blocks of Taylor series, power series. When we take the integer powers of x and create infinite series that converge to functions that we know. So we really do need to know a bit about the derivative of the power function. And so to do that, we're going to look at just x, first degree power function. Then we're going to look at an example of a power function with a fractional power and work it out, and then expose the idea that we might have what we call a power rule that will actually lend ease to computing derivatives of power functions. So in this case, we will set f equal to x. That is basically the identity function. And in this case, we don't worry about restricting the domain. We'll just say x is a real number. And in other words, the domain of f we'll just take to be all reals. Also, we know this is a very good example of an odd function. We've already proven that the derivative of an even function is an odd function, and you should look at the case where you take the derivative of the odd function and then get the even function. Now, of course, using the definition requires more subtle work with pluses and minuses. And we'll find easier ways to do that later, but it certainly sounds or seems very intuitive when you think about function graphs of even and odd functions and how the derivative reacts to that. It's just a fascinating result. So now take, again, C to be in the domain of f, just a real number. So remember, this definition is very useful. It's easy to use and it's less cluttered. So now f prime of C will be the limit as x approaches C of f of x minus f of C divided by x minus C. And so we just fill it in like we did before. So f of x is x by definition. And of course, f of C is just C upon substitution. Now, of course, this is well defined. X minus C is not zero. We don't have indeterminacy because x is merely approaching C. And so these absorb, and we just get 1 as the function. And then, of course, now we're back to this. The limit of constant is said constant. X is approaching C, but this is just 1. So now when we think of this, we say f prime of x is just 1. Or if you want to write x prime equals 1. So again, intuitively, geometrically, we think of the graph of the identity function as being a line through the origin with slope 1 for all x. So again, it makes sense that if we compute the derivative, we just get the value 1 because that defines the tangent line. I mean, the function is its own tangent line. Obviously, we think of more fascinating and interesting functions that have curvature, and that'll be something we study in Calculus 3. And when you think about quadratics, higher order polynomials, integer polynomials, and then fractional powers, you get very interesting curves. And then, of course, the lines of tangency are much more robust. But what's important here is these are building blocks. So we have to look at these very extreme cases and cover those first. Very simple, not nearly as complicated as the concept of continuity, intermediate value theorem. I mean, we left and right derivatives. I mean, we've done quite a bit of work that can get tedious, infinite limits, lots of arithmetic. But even though this is very straightforward, it is fundamental and extremely important. So we want to think about the geometric significance and the arithmetic significance. Now, what I wanted to do, there are instances when you can always use the definition of limit. We want to think about power functions maybe that are a little bit more general, but a specific case. So let's consider a power function that has a fractional power, x to the 1/3. So here's an example. And I've actually written this up, and I'll share this with you, but I just want to get the preliminaries down. So again, this is a power function. And then, of course, unlike the square root function, there is no restriction on x. We could just take the domain of f to be unrestricted. That is all real numbers. And then, of course, when we think of the power function, x to the 1/3, this is one of the family, it's a member of the family of functions that you study when you do college algebra and the pre-cal. And it has the interesting shape. I mean, I just, kind of an approximate shape here. So we have y equal x to the 1/3. Now, what's interesting about this, even though you're thinking, well, it looks like you drew a vertical tangent at the origin. Well, my picture's not so great. It is vertical there and a little bit more like this. But the idea is that we know the basic shape of the, say, cubic function, or the cube root function, excuse me. And we've lived with it a lot because we've just seen it a lot. We've seen it sketched on the board. We see it in textbooks. And so we think of it as like a parent function. And then, of course, in the prerequisite courses, we move it around, so to speak, right, left, up, down. Maybe we compress it, stretch it. In a more advanced course in pre-calculus, we can do rotations. The idea is that this becomes a building block curve. But when we start thinking about tangents here, we certainly have a more robust situation because the tangent lines will be very interesting in the sense that though we have an odd function here, we're thinking maybe here the tangent line at this point would have the same slope as a tangent line at this point. I mean, just looking at the fact that the function has symmetry relative to the origin, but not simple. We wouldn't think of the derivative as being simple as it was for f of x equal a constant or f of x equal x, the identity function. So if we apply the definition of derivative, we, just like with the square roots, we have to be fairly clever. We applied a conjugate method. So the question would be f prime of x is what? We know we can take cube roots of anything. So what is that answer? And what's interesting about this is that it just takes a little bit of ingenuity, but not a lot. So what I did with this example is I remember examples that I've taught in pre-calculus where where we made an effort to undo a problem. That is using a very convenient expression of 1 to eradicate a problem with the indeterminacy of the derivative definition. So what I've got here is basically an algebraic technique. But look, we take C to be a real number and we just form this difference quotient. But of course, at that point, we're thinking, okay, well, you know, we're going to have to get rid of that X minus C in the denominator. We must absorb that if we're going to have any hope of computing this limit. Now, what you can do here, you know that you're going to have more than two terms in the expression that you use. Mainly because if you think about this, we need an X and we need a C. So in order to get that, we've got to have an X to the 2/3 hitting this and a C to the 2/3 hitting this. So we will get an X minus C. And so you can actually use that fact with coefficients and figure out what the middle term has to be. And it's not that complicated. So what you see is you get these two terms, which are required, and then the gap term, again, you've got the minus here, you want to absorb the other terms that will so-called get in the way. So we can use X to the 1/3, C to the 1/3. And I think what's interesting about this is that algebra doesn't necessarily require so much tedium as it does just thinking about working backwards. If we're trying to prove a formula, then we might try to take it and run it backwards and see, well, where's the origin? What are we putting together? So now, if you notice this, we're thinking, okay, well, this term will give us what we need. And then, of course, downstairs, we won't have any problem letting X pass to C because this, of course, will be well defined. So now what you can see is you multiply here. We'll do multiplication by X to the 1/3. We get the X. Then we get, if you will, we have X to the 2/3, C to the 1/3. So what I've done here, and it's kind of interesting, if you look at this part here, as we multiply by this, the 1/3 and 1/3 add and give us X to the 2/3, C to the 1/3. Then we move to here, then we have X to the 1/3, C to the 2/3. That is hitting the X to the 1/3 with these three terms. And then, of course, now we have the negative. So we're going to have C to the 1/3, X to the 2/3 with the negative. And then we're going to have C to the 2/3, and then X to the 1/3 here with the negative. And then the very last term is what gives us the minus C because we have the 1/3 plus the 2/3, which gives us C to the 1. But now I probably could have used different color boxes here, but now we see that the X to the 1/3, C to the 2/3 absorb, they're equal and opposite. And then the X to the 2/3, C to the 1/3 equal and opposite absorb. So now, again, that's the key because what's left behind, the X minus C. Remember, when you're computing limits, we're not now looking at the original function. We're looking at the difference quotient. The difference quotient has indeterminacy. So just to remind you, so you don't think we're forgetting about this, when we think of the definition of derivative, from the start, the definition is indeterminate. It's amazing how we get so much output from something that starts in a very precarious form. And so just by utilizing this mechanism, we see that the extra terms absorb and we're left with the X minus C. So as we move to the next level, we have X minus C downstairs times the three terms that are like the magic application, so to speak, the X minus C times X to the 2/3 plus X to the 1/3, C to the 1/3 plus C to the 2/3. And then, of course, we're left with the x minus c here, and then of course the x minus c is absorbed. And now, of course, down here, I'll go ahead and put more parentheses here, if you like. We're left with these three terms. Now, of course, these are algebraic functions. They are continuous where they're defined. We know that when we take limits of algebraic functions, that's just direct substitution. Of course, we're not dividing by zero here, unless we just kind of look at this and say, okay, well, what is the issue here? And so we're thinking, you know, you kind of hit the nail right on the head. Let's go ahead and allow x to pass to c, right? So at this point, we just do direct substitution. So we just replace, just like I was teaching my pre-cal students today, I said, we're going to take a limit, replace x with c. And of course, they're not savvy of all the results that you now know in calculus, but I try to get my calculus students ready for what's to come. And so they did the same thing with a square root type example where they just did some conjugation methods to simplify something. And so now as x approaches c, we just do the replacement. We have what? C to the 2/3, and then of course we have a c to the 1/3, c to the 1/3 here, and c to the 2/3. But these are all copies of c to the 2/3. And we have three of them. Okay, so that is exactly why I like this form of the derivative. It is very clean, it is very efficient, and the arithmetic is easy to use as we continue to do more with the theory of the derivative. Now, if you will, you can just say, okay, well, I'll just go ahead and bring the c to the 2/3 upstairs and the 1/3 right here. And so I've got 1/3 c to the negative 2/3. And what I've written here is evidence of a general power rule. Okay, this is a remarkable example of a more general result. And you could look in your lecture notes to see the result for positive integers. It's simple to prove, much more easy than this. This requires some ingenuity. I mean, where was my, oh yeah. When I was preparing for this, I was scratching out what I needed to do here. And I have another, where's the other thing? I think I may have, what did I do with that? I wanted to show you some of my calculations if I kept it. That may have been it. I think there was another sheet I had somewhere. If I can't find it, I won't worry about it. Oh yeah, here we go. This was an initial attempt, but notice here, this is what I was talking about. I thought this would be good for my students. So what I just did is I started out with a C. Of course, I'm using a C. And so you just simply multiply by coefficients, realizing that the A and D must be these two terms, as I have already discussed. And then you can see what the B needs to be so that these terms absorb. So this is how you would set up an algorithm to do this. It's not difficult. It just requires a little bit of planning. So that was the issue there. Now, if you look closely at this, we can compare this to the original function, and this is where the general rule comes in. For right now, in this course, we will apply this rule to power functions that have integer powers and rational powers. And so what's going to happen if you compare here, it appears that the 1/3 moves to the coefficient. And then we subtract 1 from 1/3 to get a negative 2/3. So that gives you some idea about the power rule. Now, one thing I was noticing here, as you said, well, as long as we don't divide by zero, that was letting the cat out of the bag. So when you look here and you look back at our picture here, we have the vertical tangent here. I mean, we thought we had a vertical tangent. I drew it that way or tried to draw it that way, but I did not know that with what we learned from pre-cal. So what we see here is that the the derivative does not exist at the origin. And that is basically spelled out by the fact that this particular object is not defined at 0. So again, this makes perfect sense as to why our picture looks like this, at least at the origin. There are going to be other things that we're going to glean from the derivative that tell us basically why this picture looks this way at all. So not only do we get the additional information, that is, we have the set of differentiability would just be all real numbers except what? 0. So we say f prime exists for C. We can just write, we'll be lazy, just do C minus the origin. Now, in order to think of the particular derivative as a function, as a machine, we can replace now, I mean, we go forwards to go backwards, replace C with X. And so now we could say f prime as a function of X will be 1/3 X, trying to write C again, X to the negative 2/3, just like that. So now what we're thinking of is like, oh, okay, well, let's just look at this a little bit differently and maybe do a little bit of work on it. Let's just say we've got 1/3, and then we'll have, say, X to the negative 1/3, and then bring the 2 outside like that. And then let me move this up here so you can see it. So now let's just notice this is an odd function, just like f of x equal x, and then we see we have an even function here. So again, the square here kind of opens the door to say, oh yeah, this is an even function, but we know it is by the theorem. But now I'm just trying to make it look like it's even, be more apparent that it's even. So when we look at this particular example, which I think really gives you a reason to look for a more general understanding, we can say this. Now this this doesn't imply, but now we have a what we call a power rule. So in order to get other parts of this rule substantiated, in the notes we have the positive integers, and then of course as we learn the quotient rule, then we can get the negative integers, and then of course as we learn implicit differentiation, we can get the rational numbers, and then all that will be left will be numbers that don't fall into those categories. So again, it's all in building blocks, but it's so good to have an example that says, wow, look at what's going on here. We're bringing the power down and subtracting 1. So for instance, if n is a rational number, then, and of course, we always overlook the 1 just because it's, x to the 0 defining to be 1 as long as x is not 0. But we just kind of get rid of that case and then use this for numbers that have more command, so to speak, larger integers, fractional exponents. So in this case, we say x to the n prime will now just be n times x to the n minus 1. We've already dealt with the case when n is equal to 1, so we just use this for all the others. But there's nothing wrong with defining x to the 0 to be 1 for x non-zero. That makes perfect sense. But now this is what we call the power rule for the derivative of power functions. So we get, again, power rule. Maybe that's a lousy way to define it because we say power rule, do we mean the laws of exponents, the power laws or whatever? So we abuse the language and call, things by the same description, and maybe that is not the best, but we live with it and just always look at context. So now at this point, you don't have to use your calculation prowess to compute derivatives of power functions. For this, you can go ahead and apply this rule. And it's easy to apply, and you can dress it up and work with it to make it more efficient when you need to solve equations or work with things on an arithmetic level. Basically, like I've done here, you can leave the power in the denominator. You can do this, whatever is best for the equations or the work that you're trying to do. So that is an amazing result and will be a time saver for you as you continue your work in the calculus. Now, what we want to do is look at, as I look here at the list, let's go ahead and look at some of the very simple rules that now we can use. For instance, when it comes to functions that have derivatives that are multiplied by constants. And then, of course, if we had a sum of two functions that had derivatives, could we use linearity? That is, if we can extract a constant, that is a form of linearity. If we if we can actually apply the derivative to a sum and write that as the sum of derivatives, that's the second component of linearity. So the derivative actually has that those two properties. So in this case, let's just do this number one. We'll say, suppose f is differentiable on, I guess we'll just say an interval I. It has some set of content for its derivative. And we will fix, I'll just, fix a number besides C, since that's part of the derivative. We'll just say fix alpha element of R. So now when you look at this, you're thinking, okay, well, how am I going to compute the derivative of alpha times F? So now we'll say the limit, and let me not write this yet. Let me put the other idea there. We'll take the derivative of alpha times F evaluated at C. That's our definition. That's how we say, how can we take the derivative of the constant times the function that has a derivative at C? So again, in order to do that, we'll also say take C in the domain. So the assumption is that we are taking an element in the domain, at least the domain of differentiability. So that means that we have a point for which the function has a derivative. Okay, so we're not like guessing at this point. This is like, we know this because we're assuming this. So this will say, this is the limit as x approaches C of, now we have alpha F evaluated at x minus alpha F evaluated at C divided by x minus C. That's how we write the definition of derivative. But of course, this is a college algebra problem too, because we know that a constant multiple of a function is just the constant times the function. That's how we define it. It's not more elaborate than that. So we have the limit as x approaches c. And these are very simple, but they're very fundamental. That's why we go through these. Algebra, lots of algebra and lots of just notation and things, usually just long-winded. That's not an issue. We can always fill in details there. But when it comes to the basics here, this is really fundamental and we need to understand it. At least because there's more subtlety going on here. Algebra, students are really good at putting things together, adding like terms, factoring. That's something you've been doing for a while, but this is new. So now this is what alpha times f of x. That's the definition. Minus alpha times f of c. So if you want to put a little dot there just to say multiplication, just to make it really emphasize that idea, that's the definition of a constant multiple of a function. And then, of course, downstairs we have x minus c. But now note, the alpha multiplies both of these terms, and so it can be factored because we're taking a limit. So let's factor this. If you want, you can just put boxes here to say we've got this common factor. And so this will be alpha times the limit as x approaches c of f of x minus f of c divided by x minus c. Now, of course, at this point, we're pretty much done because now this just defines f prime of c by definition. So this equals alpha times f prime at c. So what we're noticing here is that if we are taking the derivative of a constant multiple of a differentiable function, we simply differentiate the function and multiply by the constant. So that just means as you're doing a derivative, you can factor constants, leave them to the side, do any calculation, and then multiply at the end. Unfortunately, we often factor constants like we're doing limits, and then we forget about them, okay? The constants do not impact zeros of the function, but they can impact the sign. Because if they carry a sign, that is definitely like a negative. That's something you don't want to leave out. So now we see that we do have the linearity with the constant, just like we have with limits. When you have the limit, you can factor constants. There is no impact. For instance, if you've got x approaching some number, the constants are not affected by the x. So this is pretty much the same thing going on here. So there's a rule that can be of use to you as you compute derivatives and take advantage of it. Now, the second one is just likewise simple. Now we're going to suppose f and g are differentiable. That is, in this case, what we want to say, differentiable on an interval, on a common interval. So for instance, if we want to be able to add or subtract them, we need to find a set for which both have derivatives. So are differentiable on an interval I. So now when we look at this, we're thinking, okay, so we'll look at the difference. You can do the sum if you like. So what we want to do is take C in I. And we're interested, for instance, if we take the difference of the two functions, how could we compute the derivative of that? Is that like limits? Can we do the same thing we do with limits? So we'll write it. So we'll say f, and of course I'm going to do the difference just to do it. So let me put the minus sign instead of the plus. So this is basically going to say, what is the derivative of the difference of f and g at c? Okay, so now we just write the definition. X approaches C. And of course, we'll have F minus G evaluated at X. So remember, we take the function evaluated at X and we subtract the function evaluated at C. And we divide by X minus C. Now, when we think about the level of abstraction, ladies and gentlemen, it is extremely powerful. The abstraction will present results that cover a wide range of functions. Because if we think of having to figure out a power rule for every possible power function, what we're looking for is a general result. So we don't have to apply the definition every time. We want a general result that allows us to move our calculations forward quickly and accurately. And so that's really what this is doing. So now, again, in college algebra, we know that the difference of two functions is just simply the difference of f of x and g of x. It's pointwise, just like we had in the previous example. So the difference function is just a pointwise difference between functions. So we write that. So this is the limit as x approaches c of f of x minus g of x. Okay, f of x minus g of x. Now let's go over here. So we have minus f of c minus g of c. So again, it's a pointwise definition. Okay? So now we'll just go ahead and do some algebra, and you can see here that we want to pair the f's, and then we'll pair the g's and we'll factor the negative using some obvious algebra. So now we have the limit as x approaches c, and we'll say f of x minus f of c, and then we'll factor the negative here, so we'll have negative g of x, and factor the negative here and leave that one in, minus g of c, divided by x minus c. So now we're thinking, okay, well, what's the next step? We'll write this fraction as two pieces. So this gives us the limit as x approaches c of f of x minus f of c divided by x minus c minus g of x minus g of c divided by x minus c. So these are good examples of using the properties of limits and then also using the definition of derivative that help you to be more confident with your calculations. So now notice, and I put the minus here very clearly, we have the limit of the difference, which is now the difference of limits. And we know that each of these limits exists by hypothesis. So now this will be the limit as x approaches c of f of x minus f of c divided by x minus c minus, and of course we can go ahead and factor the negative. I mean, we can do that because it's a property of the limit. X approaches c of g of x minus g of c divided by x minus c. So now we've got, and of course you can put parentheses here, but it's clear that we're taking the limit of this difference quotient, just like we write here, okay, and we've written up here. So now, by hypothesis, we know that this defines, or by definition, this defines the derivative of f at c, and this defines the derivative of g at c. But by hypothesis, we know that they are both differentiable on I. as C is an element of I, we know that F prime of C exists and G prime of C exists. So this equals F prime of C minus G prime of C. So when you think about this result, it's just like the last one. And what it means is that when you are applying the derivative and you have some rules in your back pocket, you can apply the derivative to each function in sum and difference separately. Okay, you don't combine them and think, well, how do I take the derivative of this? You say, well, this function f is this function g is this. I apply the derivative process here, which I know. I apply the derivative process here because they're functions that you recognize, you apply the result. And then you combine them arithmetically. So the operation of differentiation is convenient because it mimics that of the limit. That is, we can factor constants, and if we need to take the derivative of a sum or a difference, we can add or subtract the derivatives, just like we do with limits. That is very powerful. So, and of course, this can be extended by induction. If you've got the sum of 3 or 4 functions, you can simply apply the derivative to each of the function and then add them up, and you're done. So that is a significant property of differentiation that mimics that of the limits. So again, something you can use that you can apply as you do your problems. So as you learn more and more differentiation rules, then these become more and more powerful, just like you're working in a physics class or an engineering class. You will start to apply these rules even without thinking about it. They'll be that natural. Now, like I said before, 2 important functions in our study of the calculus are sine and cosine. So what I want to do is let's figure out the derivative of sine. And you're starting to think, okay, well, I can add 2 functions and I can take the derivative separately and add that result, those 2 results. Okay, but you're probably thinking, we kind of need to know how to differentiate products and quotients. That would be convenient because, tangent sine over cosine. I mean, that, we kind of need to know how to do that. So there will be results very soon about those types of functions. And then you're thinking in your mind's eye, because you've already been reviewing compositions with the continuity, because we have the composition result that impacts the continuity. That is, we've got the limit of a composition. We have the composition of continuous functions. It's continuous. I mean, very, very nice results. So you've already been looking at that. So in your mind's eye, you're thinking, well, I would probably be benefited if I knew how to differentiate a composition. Is there a theorem that allows me to do that? And there is. So it's actually to let the cat out of the bag. It's termed the chain rule. So there will be more and more theoretical devices that allow us to compute derivatives very accurately and effectively. And the one thing that we will spend most of our time doing is just like with the limits, lots of algebra, lots of arithmetic to clean up the process so we can then analyze it like we did in college algebra and pre-calc. So just remember, we're building the process. As they always say, these are small steps, or sometimes students say baby steps, because slowly but surely we're building the scaffolding. So right now, what we want to do is consider, and this is pretty simple, consider sine x. And then the question would be this. For instance, now take C to be a real number, because the sine function, as we know from trigonometry, is defined for all real numbers. And then we're interested in the following. That is, compute the derivative of sine at C. Okay, and so we're like, all right, so we gotta look at the difference quotient again. But now what I want to discuss, and if you look in the lecture notes, you see this, but this is a good review of some of the identities from trigonometry. So let's consider, so we're thinking we're going to need sine of x minus sine of c, but that's not an identity that we're just like, rolling off our tongue. So for instance, we could say at this point, let's just look at some addition formulas with A's and B's, and then we'll rig them. Sometimes this is worth going through. So this is sine of A. These are our companion formulas. We never forget these, or try not to. Sine A cosine B plus sine B cosine A. And then sine of A minus B gives us sine A cosine B minus sine B cosine A. Okay, so we're looking for the difference of two sine functions. So this is going to imply that sine of A plus B minus sine of A minus B will equal, of course, when we subtract, these two absorb, but these add, minus the additive inverse. So this gives us 2 sine B cosine A. Now, what we want to do is just make a change of variable. So we will set, this is what you did in pre-cal. It's been a while though. Set alpha equal to A plus B and beta equal to A minus B. Then, if we look here, A plus B, if you add these, that is the key here is that we can actually solve, but what we want to do, we want to find some way to replace these, and of course now then A plus B is alpha. Here, let me write this. Let me not do this yet. Then here's what I wanted to say. Gosh, I know what A plus B is. That's alpha. Then A equals what? Let's figure this out. So if we add both of these, alpha plus beta, the B's absorb, and we have 2 copies of A, so we divide by 2. Yeah, that's something we need. And B, for instance, now if we subtract alpha and beta, the A's absorb, and then we get B minus the negative B, which gives us 2B. So we'll say alpha minus beta divided by 2. Okay, so that transforms this. So equivalently, in a form that's going to help us solve this problem, we'll have sine of alpha minus sine of beta equals, now we've got 2, you can do the cosine first, cosine alpha plus beta over 2 sine alpha minus beta over 2. Now, of course, it doesn't matter what letters you use, just don't use the same letter twice. And so now we have a configuration that will mesh with the form of derivative that we're using, okay? So, like we said before, we take C, element of R. So by definition, we'll have sine, the derivative of sine, evaluated at C. Well, this will equal the limit. And of course, now we'll have letters, we'll replace alpha with X and beta with C clearly. So the limit as X approaches C of sine of X minus sine of C divided by X minus C. Now, like I say before, many times we don't always go through each step of these because the steps are simple, just lots of writing. You know, sometimes with limits, it's just the same calculation over and over. But these calculations are not as known to you. They're a little bit more complicated. And so we really do need to do them because they're going to come back as we do more calculations. So now, like I said before, set alpha equal to x and beta equal to c. Now let's do some computations. So alpha plus beta over 2 equals x plus c over 2. Let's go ahead and do this calculation. And alpha minus beta over 2 will be x minus c over 2. And then we'll get to use a special limit. So this is now what we can fill in. So, and then of course with this identity. So now, notice we have this identity, which is really what we need algebraically. So we have this equals the limit as x approaches c. So we have our 2, so we go to the right-hand side here, 2. And if you like, you know, we'll still put the x minus c down there. We have room for it. So we have 2 cosine alpha plus beta over 2, which is x plus c over 2. And then we have sine of x minus c over 2. So we do need that x minus c right there, divided by x minus c. So what's nice about this is that we have all the ingredients to make this work. But one thing that's really important here is, like I said before, notice x is approaching c, so the argument of sine is going to 0, and that's a special limit. But now notice the x minus c here is not quite x minus c divided by 2, but we have a 2 here, so we can just bring it downstairs, divide, you know, what is it? 2 equals 1 over 1 over 2. We'll use that identity. So now we'll have the limit, to use that 2 there, the limit as x approaches c of cosine of x plus c over 2. And then I'll put a little dot here, sine of x minus c over 2 divided by x minus c over 2. So like I said, when we do the special limit, sine x over x as x approaches 0, the argument and the expression in the denominator must both go to 0, and they must be identical. Okay, so we can't fudge with that. We gotta be right. And of course that 2 is there to be used. So now what do? Well, we have the limit of a product is the product of limits, which again, you know, we rely on it. And especially when we're doing the more theoretical calculations, the abstraction of these theoretical results are indispensable. That's, ladies and gentlemen, that is the reason that calculus has proliferated, mathematics in general has proliferated due to the abstraction. We think about the function and it's being the most important abstraction in all of mathematics. We deal on a level outside of our realm and figure out things and then bring it back and say, look what we can do. So the abstraction is extremely important. We still get our hands dirty with all kinds of calculations and things, but at least we know these calculations will go somewhere. So now we've got this limit, and then we have the limit as x approaches c of sine of x minus c over 2 divided by x minus c over 2. So the limit of a product is the product of limits. And we can do both of these limits. This is our special limit right here. This equals 1. That's our bread and butter. That's a very important limit. So I just wrote that there just to remind you of that. And then, of course, we can just do this by direct substitution. So we have cosine. And, of course, we replace x with c. So we get C plus C over 2 times 1. And so now, notice, even better, we have cosine of 2C over 2 times 1. The 2's absorbed, and we just get cosine of C. So now we're thinking, well, we're in really great shape. The derivative of sine at C is just cosine of C. And cosine is defined for all C. And we'll say valid for C element of R. So we can take the derivative at sine for any value of C. And therefore now we can just, if you like, we can just replace the C with X. So this implies the derivative just as a function of X, evaluated at X, is just cosine of X. That's a major result. So again, this form of the derivative is very elegant and gives you excellent results. And likewise, I'll just say in a similar manner, and this is what always bothers students, in a similar manner, we don't get as beautiful as a formula. The derivative of cosine at X using the same technique, and now you would be using the addition formulas for cosine. Same thing, it's just the same procedure as we've done up here, but we will deal with the cosine addition formulas. And this gives you the additive inverse of sine at X. So we often say the derivative of sine is cosine. The derivative of cosine is negative sine. You get the additive inverse. So that's kind of the key in all of this. Of course, the hyperbolic sine and cosine don't have this. They both no additive inverse. So, but that is what it is. But the main thing here is that you have formulas here that are user-friendly, and if you remember these, then you can get the derivatives for the other 4 trig functions. And also, when we start to anti-differentiate, I always remind students, just basically memorize or remember these, and then you'll always get the anti-derivatives correct. You don't feel, I look at it this way, there's certain things you should remember, but knowing certain details will allow you to get other details without too much effort. So the main thing about what we have learned today is that we have some very efficient rules for computing derivatives. We know that the derivative of a constant is 0, the derivative of X is 1. And then the power rule says we can simply take the power for rational powers, integer powers, take the power down and subtract 1 from that original power and get the derivative of the power function. That is amazing. That's what we term the power rule. And then, of course, we can take derivatives of sums. We can take derivatives of constant multiples using the similar tactic that we have with limits. And now, as I've shown you, just using the definition of derivative, we see that the derivative of the sine function is actually the cosine function. So remember with our definition, we are computing a derivative at a point, okay? And then the idea is to analyze this to say, where does this make sense? Now, there'll be times when we compute derivatives and we're going to just think of the derivative as a function like we have here. It just depends on the context. So when we use our second or our alternative definition, we get the derivative at a point and then we generalize to the function. So there are instances where we are going to focus on the derivative as a function. And then there'll be cases where we're going to be focusing on the derivative basically as, okay, what's the derivative at this point? We need the equation of the tangent line. Now, one thing I wanted to say in closing is this. Since the derivative of a function defines the slope of the tangent line where it's defined, that gives us an algebraic method. So for instance, here's an example that I often use in my pre-calculus classes when I'm trying to show them how to do difference quotients. And we have f of x equals 2x divided by the square root of x minus 3. Okay, well here, clearly the domain of f, you could just use the continuity result. Clearly this function is continuous where it's defined, and so for any x bigger than 3, this would work. So the square root determines the domain. Now, what's interesting here, if you apply the definition, f prime evaluated at a c, so take c in the real numbers, and you can work through this. This is a little bit more long-winded because the radical is in the denominator, but it works with the conjugate method. You just want to get a common denominator, clean up things, pull out the things that don't work in the conjugate method, then do your conjugate method, and then absorb the x minus c, which is the culprit, right? That's what is making the indeterminacy, just be in front of you like, okay, I got to get rid of this x minus c or I don't get a limit. And so here, the computation looks like this: c minus 6. This is kind of like a power rule problem. Well, it's exactly a power rule problem, so it shouldn't look weird to you when I write down the answer. And let's see here, this is a 3/2. So you can kind of look at this and say, if you took the negative 1/2 upstairs, and did your power rule, I mean, it's 1/2 downstairs and then subtracted 1, maybe this is kind of looking like a power rule. This function actually requires 2 different theorems, a quotient rule and a chain rule. But what's interesting about this, when you just apply the definition, so this is applying the definition. So try this. It's another good example of using our alternative form for the derivative. And so now we'll say, in this case, f prime exists for, and then of course we look at this, there are no additional restrictions. We still are good here. F prime exists for c, the element of 3 to infinity. And notice, f has a horizontal tangent line at 6. Why is that? Well, that means the derivative is 0. But when we look at this particular function, this quotient, it is 0 when c is 0. So for instance, if we think of this as a function, it accomplishes the same thing. But we know that horizontal tangency means that f prime is 0 because f prime defines the slope of the tangent line. Okay, so now we can see that when we compute derivatives, we may find some significance in what? Horizontal tangents. And we may find some significance in cases where we know that the derivative is undefined, but clearly we don't have that here. 3 is not even in the domain, so we don't even have to pay attention to the denominator. We just know that defines, just from the original function, the x equal 3 defines a vertical asymptote. So we would expect the function to become unbounded as x approaches 3 from the right. So that's old material, but still very relevant, clearly. And this will be very helpful when we actually sketch the graph of this function, which you're already starting to see in your mind. You've got this horizontal tangent, you've got the function blowing up as x approaches 3 from the right. So again, notice here that we get so much information from the derivative, and we haven't even covered all the ideas that we can get. And we're going to have many more of these. So if you like, if we wanted to look at the derivative as a function of x, we could simply replace the c's with x and do this. Okay? So again, we can think of the derivative as a machine, as a completely separate function. But we analyze the function this way so we can extrapolate the real numbers for which the tangent line exists. And this particular form of the derivative definition is extremely convenient. So I just wanted to add this piece. So when you start seeing questions about taking derivatives, you start seeing questions about horizontal tangents or points of horizontal tangency, you can see here, and we might as well look at this and say this occurs at 6. And so we could simply substitute 6 into this particular function here and have the point of horizontal tangency. So f of 6 is 2 times 6. And then, of course, we have the square root of 6 minus 3. So this gives us 2 times 3 times 2. And then, of course, we have the square root of 3 here. So the square root of 3 will absorb, as they say. So that gives us a 4 times the square root of 3. So the square root of 3 absorbs into the 3 here. And so we'll say point of horizontal tangency, that is the actual point, is 6, 4, root 3, right there. So we get just an amazing amount of information from the derivative. And now we're seeing how the derivative is going to be the window of opportunity. Okay, we know about infinite limits. We know how to figure out vertical asymptotes. We know how to figure out infinity or negative infinity. Okay, that's very useful. And now the derivative is going to give us horizontal tangents. It's also going to give us lots more information, which we will not be covering, at least in the next lecture, but lectures down the road. So we're just going to keep building and building and building all the information that we can get from the derivative. And then once we've pretty much exhausted that for this class, we'll move into some other topics. So I hope the lecture on the properties and some of the theoretical ramifications of the definition of derivative have been useful to you. I think you'll find them very, very important as you work on your homework. So practice using the definition, practice using the rules, and building your confidence, and continue to use the algebra and the arithmetic that you're developing. I know a lot of you are finding that, boy, you're having to do a lot of review. Go back and practice algebra, practice trig. That's fine. That's what every student has to do. So do not worry that sometimes it gets a little bit difficult. It's certainly something you can do. It's just a matter of reviving some of that information. Okay? Well, next time we'll continue the saga with more theorems about differentiation. Okay? I'll see you then.